so for this talk, we're actually going to be talking about foreign field arithmetic and I guess bridging blockchains. The two speakers are Anai and Joseph from O1 Labs. Good luck and welcome. And here's, I'll steal this one.
Yeah. Hello. I guess we will start. What time is it? Yeah, I guess it's fine. Yes, so welcome everyone. Thanks for attending this talk. My name's Anai Querol, and he's my colleague and coworker, Joseph Spadavecchia. We're both cryptography engineers at O1 Labs. And today we wanted to present an ongoing project, and we entitled this talk, Bridging Blockchains for In-Field Arithmetics. So I'll leave it to Joseph to explain high level what this is about.
Hi. So yeah, foreign field arithmetics, that seems like quite a low-level thing. It's also an interesting problem in cryptography. But to understand it, we want to kick things up to the high level, really high. And we also want to do a metaphor. Since we're in Lisbon, and we have these beautiful buildings, tiled buildings, they're very unique here, we thought it'd be cool to do it that way. So we'll talk about blockchains as buildings in Lisbon. So the analogy is that the bricks of the building are the blocks, and instead of verifying blocks, we're verifying the structural integrity of the building by verifying each individual brick and checking its structural integrity and getting the integrity of the whole building that way. So the problem is if there is a problem, then this is expensive to detect. So right now, on most blockchains, to get full blockchain security, peers need to connect to the blockchain and download all the blocks since last time they connected. They need to verify those blocks, and if it's a smart contract platform, then they need to rerun computations that are happening. So all of this is very expensive, and we wonder, is there a better way?
Yeah. So now I'd like to ask in the audience, feel free to just speak up if you're brave enough. So as a user, in order to verify the blockchain, it's a bit tedious to just go block by block, checking them all. So we're at ZK Summit. Do you know any idea that we could do in order to make this computation a bit easier? Yes?
I think several years ago, Opera had a solution that take a snapshot.
A snapshot?
Yeah, every a certain period of blocks, and then this snapshot, the root of this snapshot is packaged into the consensus protocol.
Okay.
So that makes things happen, but I mean, that's several years ago, so it should be better now.
Okay. Well, that was a solution, maybe a complex solution. That's not the solution that I was looking for, but thanks a lot for participating. I guess there's someone else there. Yeah, I guess that could work.
Recursive proofs of the block headers?
Yeah, you went to the very next slide. So yeah, thanks. You're a bit ahead. So yeah, actually the concept that the very basic concept that I wanted to introduce is snarks, right? We are adding snarks on top of complex computations to make the actual verification simpler, right? So we're in Lisbon. I'm sure you've seen these tiles on top of buildings. Voila. So yeah, what happens if we put a tile, like a ceramic tile, on top of that facade of the building to check the integrity of the blockchain? So if there's any problem with that building, the ceramic tile will basically break. So you, as a verifier, it will be very easy to realize if there's something wrong, because you will just spot it very quickly if the tile is broken. So this is what snarks could be used for. So this is very good for a verifier, but it's not so good for a prover, because now every time you add a new block, like a new brick to the building, you have to remove that tile entirely and build another one for the increasing computation. So that's not very good for the prover. So can we do anything better? Any idea? and I guess I don't know your name, but he suggested something which is called recursive snarks. So that's precisely the solution that I wanted to talk about. So in recursive snarks, we are trying to split that computation into incremental steps. So instead of having like a huge ceramic tile covering the whole facade, we're adding smaller tiles, like in Lisbon. So now, in recursive snarks, you have one smaller proof there, the blue one, and that tile attests for the validity not only of the current brick that you're adding to the blockchain, but it also is connected to the previous proof, like it's connected to the previous tile. So inductively, this means that one single tile, one single recursive snark, attests for the validity of the whole blockchain up until the genesis block. Okay? So this is what recursive snarks could be used for. And this is not something that we just imagined today. This is actually being used in practice. So this was all to introduce the Mina blockchain. This was the first succinct blockchain that allows verifiers and provers basically to have a proof of the whole blockchain by having one iterative step. So you just have to download one single proof, and that single proof will give you the security that the current block is fine, but also the previous proof was fine until the very end. So yeah, this is what Mina is about. And the actual tool that performs this computation is Pickles. So this is a protocol that takes care of the recursion step, and it uses the pasta curves, Pallas and Vesta, in order to provide support for the Halo 2 incrementally verifiable computation style. But the actual snark that runs inside is a Plonk-like proof system with 15-wire witness that we call kimchi. It has support for lookup and runtime tables to support more efficient computations, and a number of custom gates to extend the functionality of the type of circuits that we can prove things about. And just to give a bunch of more details, the polynomial commitment scheme inside Kimchi is based on the bulletproofs inner product argument, and this is to support fully trustless setup. And now my colleague will explain how, as a user, we can profit from these benefits.
Okay, so cool. So we have this great platform, a succinct blockchain, a great proof system that's got a trustless setup. But we want to do more than just verify transfers between users on a blockchain. We'd like to do smart contract functionality. And so for that, we've developed a tool called Snarky.js, which lets users specify essentially a zero-knowledge smart contract. And then that can be compiled down into a ZK app, which lives on the blockchain. And this has two really good features that come along with it. First is privacy. So when users interact with a zero-knowledge ZK app, then they're able to hold some information, whatever they like, private, and just generate a zero-knowledge proof that interacts with the ZK app and allows it to update the state on the blockchain. That's the first good thing, privacy. The next cool thing is that we're able to save a lot of computation. So in a normal smart contract blockchain, every time you interact with a smart contract, those instructions need to be replayed by all the nodes in the network. But in Mina, we just need to do it once. That could be by the user if it's a privacy-centric kind of interaction, or it could be done by snark workers in the network. But the point is the computation happens once to generate the proof, and then from then on, the nodes just need to verify that snark proof. So that's pretty cool. Even better, because we're doing recursive snarks, we don't have to verify individual proofs. They're all compressed into the one blockchain proof. So this is very, very efficient. So this is great. We have this cool platform. But we're still not done. And how does this relate to foreign field arithmetic? Well, that's going to begin now. So we don't want Mina to live in isolation on its own and just be this internal thing. We want it to actually be able to reach out to other blockchains and even real-world things and interact. And so this brings us to the idea of bridging. And bridging is pretty cool. And you can look at it in a lot of different ways. And in our case, we're focusing on a bridge between Mina and Ethereum. And if we look at the Ethereum side of the bridge, we have some really cool new things that are possible. Because Mina is a succinct blockchain, we're able to do really neat things like upload a proof of the Mina blockchain state into an Ethereum smart contract. So actually, within Ethereum kind of lives a Mina full node. And this is only possible because Mina is succinct. Then smart contracts on Ethereum can interoperate with Mina in a trustless and decentralized way. No trusted third parties, no committees of nodes to trust. So that's the Ethereum side, kind of injecting Mina into Ethereum. On the other side, within Mina, well, unfortunately, we can't trustlessly verify Ethereum in Mina because Ethereum isn't a succinct blockchain. So, Mina would have to download all of Ethereum, which is not going to happen. But there's still lots of really cool and useful things we can do. And one of the things we'd like to do is verify things in Ethereum. And one thing is signatures. So what we'd like to be able to do is to create a proof of the verification of an Ethereum signature in Mina. So this is the goal and the subject of this talk.
Yeah, but that's not easily done, right?
No, there's
there are problems.
Problem.
Yeah.
So yeah, so the problem is that Ethereum and Mina, they use different cryptographic primitives. In particular, they have different algebra. And so we need a way to solve this problem.
Yeah, so they're pretty incompatible in nature. So you can see that cloud, it's raining. That's a problem, but we can solve it. So yeah, let's take a look at that cloud. This incompatibility comes with the shape of an ECDSA algorithm. Elliptic curve, digital signature algorithm. So basically, we want to verify SECP256K1 ECDSA, but over pasta curves. So that sounds already a bit tricky, right? So in order to do this, we basically need support for group addition and group doubling, where the group is different to that of your own language, that of your own proof system. We will also need support for keytag, like SHA-3. This is a very snark-friendly hash function. Yeah, this is a pain. So we basically have to encode all sorts of bitwise operations, such as XOR, and bitwise rotation. This is a pain. Very simple, very fast to compute, but very difficult to verify. But this is not the focus of the talk. Instead, we want to take a look at the actual foreign field arithmetics. So in order to address group addition and group doubling, we realized that we need support for two primitives, two functionalities, which are foreign field addition and foreign field multiplication. And in particular today, we wanted to explain a bit high level what this foreign field multiplication is really about. So yeah, I'm trying to make things simple, and actually they're pretty simple. So I really hope you can follow, and if at some point you have any questions, please feel free to ask, okay? So this is the actual problem that we are facing at this point. So we have two numbers, A and B. They are 256-bit length, and we want to multiply them. That's it, okay? So we want to generate a C, and C could potentially have 512 bits. Okay, things are getting pretty long already, and this is integer multiplication. But in cryptography, we barely ever work over integers. Actually, we work over modular arithmetics. Yep. But not only that, but in foreign field arithmetics, we work over a foreign modulus. So we work over a field whose module is f, and basically this f could be larger or smaller than our native field. So in particular, for a use case in Mina and Ethereum, it happens to be the case that 256 bits for the ECDSA is 1 bit larger than the 255 bits of pasta. So yeah, there's an issue here, and it's pretty obvious. I guess anyone could say it. So we have a space problem. We have many things that do not fit in our buckets. So yeah, we basically have to find a mathematical way to solve this space issue. And we basically have two tricks that Joseph will introduce, and that will help us sort this out. Go for it.
Yeah, so yeah, as Anai said, we have two tricks. And this approach is an approach that was developed by Aztec, but we've adapted it to Kimchi. And the first trick we use is the Chinese remainder theorem. And that says that if you have two coprime values, and if the equation above holds for both of those terms, then the equation holds for their product, modulo their product. The next trick we have is we need to do arrange checks. We need to check that each side of the equation is less than the product of the moduli, n times n. So in order to do that, we do the range checks. And if that's satisfied, then this equation holds over the positive integers. So putting that together...
Yeah, so putting it all together, yeah.
We have the situation where we've done the range checks. We only need to check the equation holds modulo n, which is our native modulus, so that's cheap. We don't need to worry about that. And modulo m. So we need to find an m such that we can, when we take the product with our native modulus, we can fit all the foreign fields that we'd like to support.
And also it's cheap enough in our case.
And also cheap enough. Because if we choose, 512 bits, we end up with, well, it's a detail that isn't presented here. You end up with a lot more constraints, and it's harder and more expensive to constrain. So we need to choose something that's efficient in Kimchi, our proof system. So it turns out that 264 bits works very well for us. It covers the use cases we want. But wait a minute here. This is still bigger than our native modulus, which is 255 bits. So what's going on here? Well, that's OK, because it's less than the 512 bits if we did it in some naive way. What we do is we take the 264 bits, and we split it up into 3 limbs. And again, this 3 is something that turns out to be optimal in Kimchi. So now we've split up our foreign field elements into these 264-bit values, which are comprised out of 3 88-bit limbs. And an important thing here is that when we build out our constraints, we need each limb to fit in the native modulus, but we also need, it turns out, the product of 2 limbs to fit in the native modulus. And in this case, this is satisfied because we have 2 times 88, which is 176 bits, which also gives us plenty of space in the native modulus to do our constraining.
Yeah. So we basically have to decompose numbers and then treat the equation accordingly. So this is the equation that we really are caring about all the time. So we basically want to split those numbers into limbs. So here we have the high limb, the middle limb, and the low limb. Here I'm referring to the least significant bits on the right and the most significant bits in the left. So yeah, we basically decompose them, take the common factor, giving us the limbs position. We get that out. So we have like a nice picture of what's going on, basically. So yeah, this starts feeling a bit complex. There's a lot going on. There's a lot of multiplications. There will be lots of numbers going back and forth. So yeah, there's plenty of room for mistakes. So we have to figure out what's the right way to treat this correct so we preserve soundness and completeness. So one first step to do that is let's take a look first at the very top part. So let's take a look at what's before the equal term. So A times B plus the quotient times the foreign field. So let's take a look at that, and let's just compute that. So if we do that, we will have limbs being multiplied with each other duplicating the length of those products. So we call these terms intermediate products. This is like an auxiliary value that will help us constrain this equation correctly. You might wonder why we only have 3, because there seems to be many more operations here going on. But the good thing is that since we are doing operations modulo m, which is 2 to the 3L, anything that is larger than that is congruent modulo m. So we can basically skip that. And that's a reason that this type of constraints will be somehow efficient. That's why we chose such an m. So yeah, we basically have these guys. And in order to do the computation easier, we'll just place them nicely. Like, we will lay them out in a bitwise fashion. So yeah, this is the type of operation that we are now interested in. We basically send the result to the other side of the equal. And basically, if we're facing a real witness, then that operation should be 0, right? Because this is just the definition of the multiplication. So yeah, this is what we're looking for, and we just have to constrain that. So I think we can already see another problem, which is the same problem over and over again, which is, I know you all know, which is size, right? If we cannot have 2 to the power of 3L elements, we for sure cannot hold 2 to the power of 4L elements. So yeah, you know, we have to do something clever about this. So what can we do? Because we can only represent up to here, right? We can only fit up to here. So what can we do? We can just split. Yeah, we split. So we will split this equation into halves, bottom half and the top half. So since the whole equation should be 0, also the halves should be 0. So first we can constrain the bottom part. So we constrain that these equals 0. And then if there's any carry, which might be, we propagate it to the top half, and then also the top half will be 0. So yeah, by doing this and constraining that this is 0, and I'm purposely missing some details here to make this simpler. But the idea is that if this is 0, then you know that the foreign field multiplication equation also holds. So that was it, foreign field multiplication. But this is not the only gate that we need in order to support ECDSA. And he will be giving you some details about the rest of the gates that we had to include.
Right, cool. OK, so we have a foreign field multiplication custom gate in Kimchi. But to do the elliptic curve operations required for ECDSA, we need a lot of other custom gates. So this diagram gives you kind of a pictorial representation of some of the metrics of these new custom gates. So foreign field multiplication, this is taking up 2 rows, and it's using one 12-bit lookup that's represented as the dark blue flowered tile. Then we have a range check, a foreign field addition custom gate, which doesn't use any lookups, and it's only a single row. And then to do the range checks, we kept referring to a multi-range check. And the multi-range check is what you see at the bottom of this figure. It's 3 range checks. And each of those is range checking 88-bit values. And this requires 4 rows to do it in Kimchi. Yeah, so this gives us the gates. But on top of the gates, we have more work to do. And that is to build out the elliptic curve algorithms. So group addition and group doubling that you heard about at the beginning of the talk. So to give you an idea of the kind of costs of these things, group addition is taking 3 multiplications, 12 additions, and 12 multi-range checks for a total of 72 rows per addition. Doubling is taking 4 multiplications, 14 additions, and 16 multi-range checks for a total of 94 rows per.
Yeah, so as you can see, most of the complexity comes from the multi-range checks, and that takes most of the rows. So we're thinking about ways to optimize this. So if you have ideas, we will be open to discuss, because we want to reduce this number of rows. This is just an unoptimized version, but we're working on it. So yeah, feel free to reach out to us.
Yeah, so there we have another version. It's experimental that requires fewer multi-range checks. There's also been some interesting work published, casting out primes that we've been looking into. So this is a work in progress, but we already have implemented all the gates, and we're working on the gadgets, and then eventually building out ECDSA and Ketchak. So yeah, thank you for listening, and we're really happy to answer questions.